So 14.4 is called expected value. I think I love this section so much. I think it's actually really applicable to real life. We're going to be seeing some real life examples that actually come up in life. So I think you'll see a lot of stuff that's kind of familiar here. Okay. Essential questions here: what makes a game fair, and how can you determine whether a game is fair or not? Okay, so by games, we're talking about games where it's like like competition games where you're putting up a certain amount of money and then there's a certain prize, and we're actually going to be able to make decisions on whether you should be playing this game, putting up that money and going for the prize or not. Okay, sometimes it seems like, oh man, there's no way I'm going to win this prize, it's such small odds, but if the payout is big enough, we're going to be able to calculate if it's still a good choice. Okay, so the first thing we have here, and our kind of main definition for the whole section, is called expected value. It's the name of the section. So if a game gives payouts of a sub 1, a sub 2, so different payouts for different events with probabilities of p sub 1, p sub 2, etc., the expected value of the game is a sub 1 times p sub 1 plus a sub 2 times p sub 2 plus, and then I'm going to do a dot, 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 and I'm going to go a sub n times p sub n. So, in more kind of concrete terms here, okay, we'll write this down here. What we can say is the expected payout equals the sum of amount payout for each result times the probability of that result. Okay, so we're just going to take the probability of everything that could possibly happen, multiply each one individually with the payout that you get for that, and then add all of those together. Okay, so that's why it's so important that we did this section after probability, so we know how to find the probability of events. And so then we're just going to be able to multiply that pretty easily here. Okay. All right, so I'll give you guys another second to write that down. So we have the expected payout equals the sum of the amount payout for each result times the probability of that result. Okay, so let's take a look at a pretty simple example here. It says a die is rolled, and so a die is a 6-sided die. You get $1 for each point that shows. Okay, sounds like a good game to me. What is your expectation? Okay, so what's our expected value here? How much money can I expect to win on any one given roll? Okay, so you kind of visualize this. If you visualize the die, so if you get a 1 here, it's saying that that's going to give you $1, right? And if you get a 2, that's going to give you $2, etc. Okay, so you get the same amount of dollars as the number on the die. Okay, so what is the probability of rolling a 1? Well, the probability of rolling a 1 is 1 out of 6, right? Because there's 6 sides to the die. It's a fair die, so it could equally likely land on any one of those. And the probability of getting a 2 is also 1 over 6. And the probability of getting everything is 1 over 6, correct? Of every single individual one. So what we're saying here is that what we can expect from this is we'll get $1 for rolling a 1, and the probability of that is 1/6, correct? We'll get $2 for rolling a 2, and the probability of that is also 1/6. We'll get $3 for rolling a 3, and the probability of that is 1/6. I'm just going to do a ... here, and then we're going to keep doing that, and we'll get $6 for rolling a 6, and the probability of that is also 1/6. Now, since we're dealing with money here, I think that a decimal answer is going to be kind of a better answer for us anyway, because when we deal with money, we usually don't deal with fractions. We usually deal with decimals. So I'm just going to go ahead and type this into Desmos and see what we get. So I'm going to switch over here to my Desmos. And we'll do 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6. And this is taking a long time, so I'm actually going to copy. Can I copy paste this? Watch this. I'm going to copy paste this, and then I'm just going to change the numbers in here. So let's go 6 there. Let's go 5 there. Oops, 5 there. And let's go 4 there. Look at that. Okay, so eventually here, I got it all typed out, right? So 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. You can see that our answer there is 3.5, okay? So that's our answer to this question. We're going to analyze it here in a second, but let's just write it down for now. So on this game, we can expect to win 350. Now, it's kind of a weird answer, you might say, because is there any result that will actually give me $3.50? No, there's not, right? If I land on a 3, I'll get $3. If I land on a 4, I'll get $4, but I'll never actually get $3.50. But they're saying that if I do this kind of an infinite number of times, if I do this, let's say 1,000,000 times, I'll probably get like $3.5 million, okay? So when you expand this out into large numbers, that's kind of the average amount that you're expected to get. Now, I'd say that this result is actually not too surprising to me, because this result is actually, I'm getting $1 for 1 and I'm getting $6 for 6. This is actually the number that's directly in between 1 and 6, if you think about it, right? Yeah, because if I start at 1, I go 2 over, I'm at 3. That's from 6, I go 2 over, I'm at 4. So it's like halfway in between that 350. The other way you can look at it, in this particular case, it's the average of 1 and 6, right? Like 1 plus 6 divided by 2 is 3.5 as well. So since we're getting every number along the way here, that's why that happened. We have 1, 2, 3, 4, 5, 6. We're not skipping anything. That is why that came out to the average. That won't always be the case. But when it's kind of a consecutive numbers like this, very often it is, okay? So that is our expected value from this game. We can expect to win $3.50. So sometimes we're going to win $1, sometimes we're going to win 5, sometimes we're going to win 4, but it's saying overall our average expectancy would be $3.50, okay? Okay, so these expected values here come up a lot in Vegas, okay, in like gambling games. So let's look at this one. It says here, in Monte Carlo, game of roulette is played on a wheel with slots numbered 0, 1, 2, all the way to 36, okay? So on this wheel, there is 0 through 36. I'll tell you, in Vegas, they actually have another spot. They have 0, 00, and then every number up to 36. They actually have one more than this, but in Monte Carlo, they take one away. We'll explain why that's actually better for you, that they took one away here in Monte Carlo, but let's continue here. The wheel is spun and the ball is dropped, okay? And the ball is equally likely to end up in one of the slots. So to play this game, and there are other ways to play this game, but the most basic way, you bet $1 on any number, okay? You can bet $1 on the number 23, for example, if you're a big Michael Jordan fan, okay? Or LeBron James on the Cavaliers. If the ball stops in your slot, you get $36. You get your $1 bet back plus the $35. And if it doesn't land on your slot, you lose $1, okay? So that's the rules of the game here, all right? So first thing we need to kind of analyze here is we need to understand how many slots there are, how many options there are. there's actually 37 slots. You may think 36, but if it was from 1 to 36, that would be 36, correct? And so putting the 0 there adds an extra one more than you would have thought. All right. You can also think of it, remember we used to do the sigma. I used to say n is top minus bottom plus 1. So 36 minus 0 plus 1. That's that same idea that when you're subtracting and you're counting all the numbers, there's actually an extra one there, okay? And so what this means is that since there's 37 slots, the probability of each slot would be 1 out of 37. So whatever number I pick, I have a 1 in 37 chance of winning, okay? My probability of winning is 1 over 37. However, the probability of losing, well, we remember that from the last section, complements. So the probability of losing is the probability of not winning, let's say. And you can always find the probability of a complement by subtracting it from 1, right? So if the probability of winning is 1 out of 37, that means the probability of losing is actually 36 out of 37. It's also logical if you think about it. So if one slot is a winner for me when I pick that, that means that 36 slots are losers, right? If I don't hit my number, I lost. Okay, so let's find the expected value here of the roll, okay? So here's how I'm going to calculate it. So I'm going to do the probability that I win is 1 out of 37, right? And I'm going to multiply that by how much I'm going to win. Now, how much do I actually win if I hit my slot? I'm actually going to say I win 35. Now, it said I get 36, but as it explains in the parentheses there, I get my $1 back plus an extra 35. So my actual kind of profits there would be $35. Okay? So then we're going to add that to this one. So what's the probability that I lose is 36 out of 37, right? Now a tough question. What goes in front of that? Okay, so how much money do I get if I lose? Like I said, kind of a trick question, kind of a tricky question. How much money do I get if I lose? Can anybody think of that number that would go there? You can type it in the chat. All right. I agree. We win -$1, right? Which is to say we lost $1, but that is how we kind of show losing money in math is negative numbers, right? Yeah, and I always when I used to teach like algebra 1, and students struggle with positive versus negative numbers, and they say like, oh, the answer is 5, and I'm like, no, it's actually -5, and they're like, same thing, and I'm like, no, is like winning $5 the same as losing $5. That's how I always kind of explain that. Negative numbers, think of it as like money you owe or money you lost, okay? Okay, so let's go ahead and type this in the calculator. So let me grab my Desmos here. And so I have 35 times 1 over 37 plus -1 times 36 over 37. And so we got our answer right there. I'm going to go ahead for that. I'm just going to put that's about negative 0.027. So you can expect to lose, I don't know, let's say about 3 cents every dollar you bet. It's actually a little less than 3 cents, correct? I said about, so I feel like I'm covered there. Okay, so why does this make sense? Why do you expect to lose playing roulette? Well, hey guys, you know all those casinos, those big tall buildings that they have in Vegas? They don't build those because people are winning, right? They set up these games and it's not even they're not cheating. They just set up the games and they say these are the rules and the rules give the house, the casino a slight edge over the player, okay? So I mean, if you'd like to ever, when you're 21, to go play in Las Vegas and have fun with an amount of money that you're okay with losing, I think that's fine. But I just remind people to understand that in every game, that the casino has a slight edge. They have a slight advantage. You're expected to lose. Now, back to what I was saying about in Las Vegas, they actually on this roulette wheel, they have another number here. They still only give you $35 if you win, but this is 1 out of 38 and then this one is 37 out of 38. So if we did that one, it would be even less. You'd lose even more money. It would be a bigger negative number. And so that's why Vegas it's even worse than this actually. So yeah, this is actually pretty close to what it should be. All right, let's move on to the next page. All right, so at any given time, the express checkout lane at a small supermarket has 3 shoppers in line with a probability. Wait, the express lane at a small supermarket has 3 shoppers in line with a probability of 0.2, 2 shoppers in line with a probability of 0.5, 1 shopper with a probability of 0.2, no shoppers with a probability of 0.1. If you go to this market, how many shoppers would you expect to find waiting in the checkout line? Okay, so this is not dealing with money, but it's still kind of the same the same application here, right? So our expectation of how many shoppers there, we take each individual probability and multiply it by how many shoppers are there. So the probability that there are 3 shoppers is 0.2. The probability that there are 2 shoppers is 0.5. The probability that there is 1 shopper is 0.2. And the probability that there are 0 shoppers is 0.1. This one I actually feel like I don't even need a calculator because the numbers are pretty easy here. So I'm just going to do it. So this one would be 0.6 plus 1, 0.0, or just 1, plus 0.2, and then obviously plus 0. And so 1.8, we can expect 1.8 shoppers in line. Now, they kind of report stuff like this on the news a lot or whatever. With like someone is reporting this, I don't know, a newspaper, or I guess they don't have newspapers anymore, but like, I don't know, New York Times or The Hill, or wherever you get your news, and they'll say something like this, like 1.8 people expected, blah, 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 blah. And then people will get all frustrated and say, how do you have 0.8 of a person? How do you have 1.8 of a person? And so obviously we're never going to have a time at the store, like I said, where we actually have 1.8 shoppers because it's not possible to have 0.8 of a person. But we're saying on average, if I went there, I can kind of expect 1.8. So what integer could I probably expect most often? I would probably say 2, right? But sometimes it'll be 1, so that brings the average down. Sometimes it'll be 3, so that brings the average up, and sometimes it will be 0. So it's just saying overall, you know, if I did this an infinite number of times and I found the average would be about 1.8. Okay. All right, awesome. We have this is kind of some reading here, so I'll highlight some key stuff here. So it says the methods of mathematics have recently applied to problems in social sciences. For example, how do we find fair voting methods? You may ask, what is the problem with how we vote in elections? Well, suppose candidates A, B, and C are running for president. The final vote tally is as follows. A gets 40%, B gets 39%, and C gets 21%. So candidate A wins, but 60% of voters didn't want candidate A, right? So if 40% of them voted for candidate A, that means 60% did not want them. Moreover, suppose you voted for C, but you also dislike A so much that you'd be willing to change your vote to B to avoid having A win. Suppose most of the voters who voted for C felt the same way as you do. Then we have a fair situation in which most of the voters prefer B over A, but A wins. Is that fair? So in 1950, Cannadero showed mathematically that no democratic method of voting can be completely fair, and he won the Nobel Prize for this. Mathematicians continue to work on finding fairer voting systems. The system that is most often used in federal, state, and local elections is called plurality voting. But other systems include majority voting. So if no candidate gets the majority, a runoff is held between the two top vote getters. So that's kind of a way to deal with that in that previous one. So if nobody gets over 50%, then the top two would have a runoff against each other. That's actually what happened in Georgia. If you guys heard the news on that in like January when it was so important, they had like the runoffs because they had the regular election in November, and they do a system where the top two have a runoff in a special election in January. So that's why they were having that extra election in January, okay? Preference voting. This one is actually, I see a lot of kind of people, this is like gaining some popularity here. Preference voting would be each voter orders the candidates according to their preference. So you could vote for, you rank them. And so it's not just you pick one person, you're picking, let's say if 5 people are running, you're picking the ranking for all 5. And then they would calculate, first place would be worth this many points, and it would be like on some sort of point system. People who are like third parties, so like libertarians or like Green Party people, always want this because they always feel like their candidate would get a lot of kind of second place votes or even first place votes if people could still put the candidate they didn't like all the way at the bottom, because they figure that's how most people vote, is based on who they don't like. And then cumulative voting, each voter gets as many votes as there are candidates and can give all of his or her votes to one candidate or distribute them among candidates he sees fit. So if you lose, you get to send your votes to somebody else and you get to choose it. So that's another way you could do it. The last system is often used to select corporate boards of directors, something I don't know anything about. But each system of voting has both advantages and disadvantages. So this is not to say, I don't know, well, this wasn't a political speech at all here, right? But I'm not saying that any one of these is better than the other. It's just something interesting to think about, all right? Okay, so next up, we're going to move on to something called a fair game, okay? So a fair game is a game with the expected value of 0. So we just saw the previous question with the roulette game. Was that a fair game? I would say no. It was in the negative, correct? So it was advantage to the house. So if we had a fair game, that final answer would have come out to exactly 0. Now, was that one actually pretty close to 0? It actually kind of was, right? Like 2.7 cents in one direction, I would say is not too bad. But yeah, it would be 0. So you could, you would expect to actually break even. So you actually wouldn't expect to win or lose in a fair game. The easiest example, and I don't think we have it here on our notes, but what I always think of a fair game, I think of Super Bowl squares. You guys ever play those Super Bowl squares? So on Super Bowl squares, like there's like 100 squares, and you put your name in as many as you want, and let's say you pay $1 for each square, and if like the score comes out and you win $100. So it's like everyone puts $1 in, that gets a square. If you have 100 people, everyone put $1 in, and then the $100 comes right back out. There's no house taking any money there. So even though you only have if you pick one square, you only have a 1 in 100 chance of winning. It's still a fair game because if you do win, you win $100. All right, cool. All right, let's take a look at this one though. So suppose you're playing the following game. A card is drawn from the deck. If the card is an ace, you get a payout of $10. If the card is not an ace, you have to pay $1. Okay? So, is this a fair game? So first of all, I'm going to say the probability of an ace. We kind of saw this on our last one. Remember, there's 4 aces, 1 in each suit. So that's 4 out of 52. And that is 1 out of 13 if you want to use that instead. Either way will work. We're going to type it into a calculator anyway. So then the probability of not an ace, we know, is the complement of that. So that would be either 48 out of 52, or I'm just going to use 12 out of 13 because it's a little bit easier to do 1 minus 1 out of 13, right? So your remember that your probability of something happening plus it not happening is always 1. So 1 over 13 plus 12 over 13, obviously 1, correct? Okay, so let's calculate if this is a fair game. So our expected payout, well, we're going to get $10 if we get an ace. And then we're going to lose $1 if we get anything else. All right, I'm going to go ahead and type this in the calculator. All right, so I'm getting negative 0.154, let's call it, okay? So that's about negative 0.154. So definitely not a fair game. And in fact, it's even worse than the roulette game we saw earlier, correct? Okay. So this one was really a yes or no question. Was this a fair game? We would say no, not fair. Part B, if the game is not fair, which we saw it was not, what would the payout have to be to make this a fair game? Okay, now we're talking. So we'll set this up very similar to the previous one, except what we don't know is how much should the payout be, correct? Remember in math, whatever the question is, that's always going to be our variable. So I'm going to go ahead and throw an X there. We still have to pay $1, right, if we lose. And if I'm going to put an X in that position, that should mean that I need to know the numerical value of E. And so we learned that in order to make this a fair game, the numerical value of E would have to be 0. So we're going to solve this for X. I'm going to go ahead and multiply negative 1 times 12 over 13 is just negative 12 over 13. I'm going to go ahead and add that over to the other side. So we have 12 over 13 equals X times 1 over 13. I'll go ahead and multiply this by 13 over 1 on both sides. Oops. The 13s over there cancel out. And so X would have to be a $12 payout. So if we make this a $12 payout, for if I get the ace, and still charge $1 if I don't get the ace, that is actually a perfectly fair game. So if somebody played that game an infinite number of times, they could expect to break even, have the same amount of money as they started with. All right. So if we were paying out more than $12, that would be an advantage to the player. If we're paying out less than $10, like we saw in Part A, that's an advantage to the house. All right.